Very happy to welcome Adam Śpiewak, our own Adam Śpiewak, and the title is Universal Projection Theorems Interpretations.
Thank you very much. I will talk about results from a recent prep with Balázs, Bárány, and Károly. And so, as the title says, this will be about what we have decided to call universal projection theorems and their applications. So let me begin with a very vague and very philosophical few words about what do projection theorems, or the general philosophy of what I mean behind this title means. So, well, there is a family of results in geometric measure theory and in fractal geometry and also in dynamics, which can be seen as different versions of, in some sense, a similar scheme, which I would call a projection theorem. And usually what one faces is a family of maps. So let's say that we have a family of maps from some space X, let's say to Rd. In our case, everything will be going to Rd, and assume that it is parameterized by some parameter lambda. Okay, so we have a parameterized family of maps, and philosophically speaking, what we would like to understand is to understand how geometry in this or other sense, either of the set X or maybe of its subsets, or maybe most interestingly for us today, of measures on a set X, behave under these projections. And somehow the general philosophy, which on one hand is what you often expect to be true, hence it is also what is often your goal to prove, is that for typical lambda, maybe not for all of them, but for in some sense typical lambda, the geometry of a set or maybe of a measure changes under such a map, under such a projection, let's say. But most of the time when I'm saying projection, I really just mean a map. Okay, it rarely will be, sometimes yes, but not always will be a true projection. So what we expect is that the geometry will change as little as possible. And now what does as little as possible mean? Well, this depends on the context. Okay? And now you will see a very particular example in a moment. But let me tell you right away that what we do in our work is we are interested in universal projection theorems, where this universality means that instead of a single measure on a set X, we have a whole bunch, a collection, which I will denote by M, of measures on X. Think of some big, uncountable collection of measures. And now we would like to know that for typical lambda, this expected behavior holds for all measures from your collection simultaneously. Okay, this is somehow the general philosophy, and why this is interesting and why this has some motivations. I will try to convince you during the talk. So before I get into any further details, just a short reminder, I guess, but just to make sure that we are on the same page. I will recall some basic definitions of dimensions. So dimensions of sets and measures will play a crucial role in everything that we are doing. Yeah?
I didn't understand the question. So, what do you require from measures? How they depend on lambda?
We will get there. We will get there. So, okay. So, a priori, this collection, these measures will not depend on lambda in any way. You are just given a collection of measures, and now you look at different maps from your family, and you would like to tell whether for given lambda, or in our case, whether for typical lambda, it is true that the expected behavior holds for all measures at once from M. So they don't have to depend on the parameter. In some sense, you could do so, but this is not what we are studying here. Now, so quick recap on dimensions. So we will need notions of causal dimension of Borel measures, or well, of measures. So let mu be a Borel measure on a metric space, and now we define upper and lower local dimensions via these formulas. So what we do is we look at the ratio of the logarithm of a measure in R ball to the logarithm of R. And If the limit exists, great, then this is called the local dimension of the measure at the point x. Often this limit does not exist, and then we consider upper and lower limit. And these values tell you that measure of a ball scales roughly like r to power d, where d is this local dimension. Okay? At least if the dimension exists at the limit. And now Hausdorff dimensions of a measure are defined in terms of the lower local dimension, so the lower bar, and these are respectively, the upper one is the essential supremum of the lower local dimensions, and the lower one is the essential infimum of the lower local dimensions. You could also do the same with upper local dimensions, and then you end up with what's known as packing dimensions, upper, and lower. Now, one more notion of dimension, which will be important for us, which is maybe, well, a little bit less famous as the Hausdorff dimension, but it's gaining quite some publicity recently. So this is a notion of the asphalt dimension, okay? And now, here is the definition, but maybe instead, let me try to make some picture. So you should think of it as some sort of a maybe version of the upper box counting dimension, but such that looks not only at how the covariant numbers of the whole set scale, but it also looks at how it scales locally near every point. So basically what you do is, let's say that we have our set, and then what you do is you have to fix any point in the set and look at and fix two scales. So you fix a small scale, small r, and a large scale, large r. Okay, and what you do is you look at the ball of radius capital R, and you look at small r coverings of whatever part of your set you see in this ball. Okay, so these are covers by balls of radius small r, right? And then what you do is you calculate what I denote here by n. So n is the least number of balls needed to cover this set. This set is this intersection, right? So this is whatever we see over here. And then you count the least number of balls of radius small r needed to cover this set. Okay? And this is supposed to be at most some constant, well, times the. So if you would be covering the whole set, then you would just be, then the box counting dimension would correspond to setting here large r equal to 1. But what we do is we want to rescale everything to the scale large r. Okay, so we end up with inequality levels. Sorry?
Not one, diameter of the set.
Well, it doesn't matter if you take it, then it's just up to a constant.
There is a constant n here.
There is a constant n here. So basically, what it tells you that this set roughly looks S-dimensional, but in the proper scaling, right? And that's so some say that asphalt dimension is the greatest of all dimensions because it's an upper bound for the upper and lower box counting dimensions, and also for the Hausdorff dimension. Which is not surprising because here you also, in the asphalt dimension, you have to worry about, well, what happens locally everywhere in the set, right? So these are the notions of dimensions, and there are, so I said about this general projection theorems. What we do in this paper, we have somehow two particular settings which are our motivations, orthogonal projections and iterated function systems, and then we somehow prove a general theorem that applies kind of to general projection schemes. Okay, but first, and actually I think most of the talk I will spend talking about these two particular settings. Okay, so let's begin with I guess maybe the more direct one, the orthogonal projections. So some notation. By GRDN, I will denote the Grassmannian of d-dimensional planes in Rn. So this is a compact finite dimensional manifold. It has there is a natural reference measure, a volume measure of the Grassmannian, which happens to be the unique invariant probability measure invariant under the action of the orthogonal. Okay, this is somehow the natural uniform measure of the Grassmannian, if you want. And given a plane, so an element of the Grassmannian, by PV I will denote the orthogonal projection onto this d-dimensional plane. Okay? And now here we have, I guess, the archetypical projection theorem, very classical result in geometric measure theory. This is what's often called Marstrand or Marstrand-Mattila projection theorem. Here I stated in a version for measures. Okay? So now, suppose that you have a Borel probability measure mu on Rn, and then the question is, what happens with the Hausdorff dimension of the projection of this measure? Okay, so you look, you have your measure, maybe it lives somewhere here, you fix a plane V, and you look at the orthogonal projection. Okay, and PV mu is just the projection, the push forward of mu under PV. Okay, so here we end up with some mu measure, and the question is, what happens with the dimension? And now what this theorem tells you is that maybe not for all, definitely not for all, usually, but at least for typical, in the sense of this measure eta, so for eta almost every d-dimensional plane V, the Hausdorff dimension, both upper and lower, possibly drops, but drops only as much as necessary. What does it mean? It means that the dimension of the projection is equal to the minimum of D, so the dimension onto which we project, and the dimension of the original measure. Okay? So the way to think about it is that we always have an inequality. So the dimension of the projected measure is always at most D and at most the dimension of the original measure. So it's at most the dimension of the original measure because projections are Lipschitz, and Lipschitz maps can only decrease the Hausdorff dimension. And well, this measure lives on a d-dimensional space, so it would have a hard time having dimension greater than D. So this is why we have the other upper bound. And the theorem tells you that typically this upper bound will be achieved. Okay, so well, geometry gets preserved as much as possible in a sense that the dimension doesn't drop more than it has to. Okay? And if D is greater than the dimension of the original measure, then the dimension just gets preserved. And now, the question that we are interested in this context is the question, well, what if now instead of a single measure, we have a family M of measures on Rn? And the question is, can we find conditions on M such that, well, so here I have stated it formally, so we want to check whether the eta measure of the projections for which there exists at least one measure in this family for which the dimension drops, the dimension formula does not hold, does this set have measure 0, okay? Which simply means that so from this theorem we know that for every mu, there is a full measure set of projections on which the dimension gets preserved. But if the family M is uncountable, then we don't have a guarantee that we can take a common full measure set which works for all measures in the family. Okay? And it's certainly true, well, it's certainly so that we have to impose some conditions on M, right? This will not hold just for any M, and there is a trivial example here. What you do is, for example, you can just take on the plane, let's say unit intervals going through 0, well, in all the possible directions, right? And then you see and take uniform measures of those, and then you see that for any such interval, if you project onto the orthogonal direction, the uniform measure gets squeezed to a Dirac's delta, and the dimension drops from 1 to 0. Okay, and then, so this means that for every measure in this family, if we look at all the possible intervals like this, then actually for every direction there is a measure whose dimension drops. Okay, so it's a non-trivial question in a sense that, well, definitely if we want to prove something like this, we have to pose some conditions on M, and we find such a sufficient condition. And as an application, so let me tell you right away, this will be kind of a spoiler, but just to set our mind, we can indeed prove such a universal version of Marston's-Mattila theorem for families of measures which are arising from iterated function systems. So, in particular, if you take as M, so what you do is you can fix a self-conformal IFS or a conformal IFS on Rn. If you don't know what it means, we will get there later. So all of this will be defined. But for those of you who are familiar with this, we can fix a conformal IFS, look at its attractor, which is a self-conformal set, and if this IFS has strong separation, then we can prove that this universal thing holds for all ergodic measures at once. Okay? And this is definitely, so these are ergodic measures from the symbolic space. This is definitely a big uncountable family of measures. And again, if you are uncertain what precisely this means, we will get there soon. Another, yes?
So if I try to think about it as thinking about the measure also as a parameter,
yes,
thinking about the projected theorem which is on a bigger space. So if we are able to prove a Marston-Mattila theorem in that setting, is this enough? Because then you need to use the Fubini.
Well, if you want to deal with all measures at once, I don't think that Fubini will give you for almost every measure, whatever it means, almost every measure. I'm not sure if I understand well enough what you mean.
I was trying to add the measure as a parameter.
Right. So then, well, right. So then, I guess if you want to, well, then to make sense of the statement, you would need to have a measure on the space of measures, right? To say that for almost every measure.
Yes, of course.
Right. And then when you use Fubini, you can only say that for typical lambda, you have it for almost every ergodic measure, whatever it means, almost every ergodic measure.
For almost every measure.
Yes.
Yeah.
Yes.
Yeah. Right. Okay.
Another class which has the advantage that does not assume any separation whatsoever on the set is the class of Gibbs measures. Okay, so this will be Gibbs measures corresponding to Helder continuous potentials on the symbolic space, and so we are unable to deal with the whole space of ergodic measures in this case without any separation, but we are able to deal still with a very large and usually kind of natural class of measures. Okay, so these are this is kind of a shortcut, a glimpse of what we can do. What we also do, in particular in the setting of orthogonal projections, is in addition to extending this classical Marston-Mattila theorem or improving it to a universal version, we can do the same with a certain result, which we have proved with Krzysztof and Jonathan some time ago, which is kind of maybe a probabilistic version of the Aswad dimension embedding theory. Okay? So let me tell you first what it says. So it says that if you fix a probability measure now with a compact support, and this compact support satisfies this. So the Aswad dimension of the support of mu is smaller than d. Okay, so now we will be projecting onto planes of dimension larger than the dimension of the measure, even larger than this, the Aswad dimension of the support. And then we can prove that for almost every projection, this projection has a property which, well, not in this paper, but now in our work with Károly and Balázs, we call mu nearly B-Lipschitz property on the support of. Okay, so the projection will be mu nearly B-Lipschitz, almost every projection. And now what does it mean to be mu nearly B-Lipschitz? Well, here is the definition. So assume that you have a Lipschitz map between two metric spaces. And now for a moment ignore whatever is here. Look at this equation, this inequality. So if this inequality would hold for all x and y with some constant c and some alpha, this would simply mean that first of all, this map F is injective and the inverse is alpha Helder. Okay? This is just what it means. Now, in this setting, we cannot claim that the projection is, well, globally alpha Helder on the support, but what we claim is that for almost every x and every alpha which is between 0 and 1, So the Helder exponent will get as close to 1 as you want, hence nearly be Lipschitz. Okay, so once more, for almost every x, for every alpha between 0 and 1, there exists a constant. But now this constant is allowed to depend both on x and alpha, such that this inequality holds for all y's. Okay, so this is a statement on the regularity of the almost surely defined, almost everywhere defined inverse to the projection map on this set. And now, of course, the question is, why bother? Why try to extend this particular result to this sort of universal version? Well, we have a reason for this. So
Lipschitz means both ways.
Well, so I just assume that the map is Lipschitz in one direction.
Ah, okay. Sorry, I didn't.
In our cases, they will be always Lipschitz, right? So this is why B Lipschitz, nearly B Lipschitz. The point is that in the other direction, it's somehow, well, at almost every point, alpha Helder with alpha as close to 1 as you wish. Maybe not equal to 1, but as close to 1 as you wish. And so, first of all, what we do is we can generalize this result, well, not in the universal version, also beyond the orthogonal projections to the setting of iterated function systems and also slightly beyond. And the point is that once we have it, we can use it to provide it has some applications to the multifractal analysis. So there will be some new results on multifractal analysis of self-similar measures, and this was one of our motivations. Now, so this was this first setting and a glimpse on the results in this case. So now let me talk about the second setting, which are the iterated function systems. So again, first I will recall some definitions. So when I say an IFS, so an iterated function system, for me this will mean a finite collection, which I denote by F, of maps. These maps are contractions on some compact set V. I assume right away that it is in RD. These are strict contractions. And A, so they are indexed by elements of set A. So A is an alphabet here. Okay? And now, some definitions. So a basic object that you can associate with such an IFS is its attractor. Right? So this is a unique, non-empty compact set lambda in V, which satisfies this equation, right, which says that lambda is equal to the union of its own images under the maps from the IFS. So in this sense, so these sets are in some sense, well, self-similar in this vague sense that the whole is composed of small pieces which resemble the whole, and the resemblance or the symmetries are given by the maps from this IFS. We will also need a symbolic space, and symbolic space is just well, this infinite product space over the alphabet. So these are just all the one-sided infinite sequences with values in the alphabet. So this enumerates all the possible, well, all the possible infinite choices of maps from the system. And what will be very important for us will be the natural projection map, which I denote by pi with index f. So this is a map which goes from sigma, the symbolic space, to V, but actually it goes onto the attractor. And this is a map which is defined in the following way. So given such an infinite sequence in omega, which should be sigma, so given such an infinite sequence, what you do is you look at first an elements of the sequence and you look at the composition of the corresponding maps, right? And then if you look, let's say, at the image of the whole space, what you obtain is a sequence of decreasing sets, right? And moreover, because of the contraction, the diameter of the set will go to 0 exponentially. So in the limit, there is a unique point. And this unique point is what, by definition, is the natural projection of the sequence omega. And a useful fact is that the attractor is equal exactly to the image of the symbolic space under the natural projection. Okay, so this means that, well, every sequence, when you do this procedure, it lands in the limit on the attractor, but also it means that every point on the attractor has at least one coding in the symbolic space. Sometimes it will have more than one coding, and this is the root of all evil and all that is interesting, I guess, at least in the settings that are interesting for us. So some pictures. I guess when we talk about iterated function systems, you are obliged to show some pictures, at least with slides. So, for example, the well-known multifractal control set is an attractor of an IFS on an interval given by this formula, and you can imagine the way maybe to imagine the natural projection map is that the system generates for you this sort of tree, where at deeper and deeper level you have many exponentially small intervals, which are the images of all the compositions, and then to find, given a symbolic sequence, an infinite symbolic sequence, what you have to do, you have to follow this tree all the way up to the limit, and in the limit you will see some point on the attractor. Right? And now this picture is without overlaps, but it works just as fine if this first level basic pieces would over. Then it still makes sense to kind of follow this path of natural projection. So now break for pictures. One picture, second picture, third picture. And here you have a real-life approximation of an attractor.
When I first time saw it in the shop, I went home with camera in the shop and made it.
But this is not your picture.
No,
No.
it is isolated. I have it with other vegetables.
I see.
Which year is this?
This picture?
This Romanesco.
Which year?
This is a guy, right? Or,
No, I think so. This
Romanian.
I think it's Mr.
Romanian cauliflower.
oh, this is a. So wait, I didn't understand. This is not a scientist
Broccoli.
called Romanesco?
No, I don't think so.
Ah,
It's just the name of a vegetable. Yes. So this let me be clear. This is not a picture of an attractor of an IFS. This is a picture of an actual broccoli, which somehow happens to resemble attractors of IFS.
I made photo in vegetable.
and you did this picture.
No, but I have my own picture of this.
Okay, so now unfortunately the picture break is done.
Vegetable to the lecture.
Really?
You show the students the
But this picture looks, it's something not natural.
Artificial, right?
Yes, it looks artificial.
I think it's just a very good picture.
Okay.
You can look at the
Okay.
bottom of this,
Yes.
Okay, let's get back to the technicalities, unfortunately. So, we will consider a certain class of IFSs, namely C1 plus theta conformal IFSs, and whenever I say C1 plus theta conformal IFS, what I mean is just that the maps in the IFS, they extend to some open neighborhood of this compact set V in such a way that they become C1 plus theta contracting maps, and moreover they are conformal, right? So at every point the derivative is a similarity. And now, a very useful notion for us, which maybe is just useful to kind of shifting your perspective in a sense, is a certain metric on the symbolic
It's good to
space.
say that in dimension bigger than 2 conformal is maybe
Right,
locally.
right.
So it's are very special, so it's not so special in dimension 1 and 2.
Yes. So somehow dimension 1, yeah. I guess in dimension 1 this is the
Dimension 1
most.
conformal says nothing, but it's C1 plus theta.
Mhm.
It's not anything.
Mhm.
In the plane is rather big. Higher dimension is good.
But here is the one included, so
Dimension 1 is included, yes. And actually, as you will see, I guess the main applications are to dimension 1. But everything, well, okay. Both the applications and the theory works in
I
higher
was
dimensions.
fighting or discussing with Mariusz Rubines in his papers. He has similar introductions to several papers. He always writes conformal, not mentioning that it is interesting. It's interesting also in high dimension, but it is very special.
So we are never using C1 plus theta and conformal in the same system. Either it is C1 plus theta when you are in dimension 1, Or it is conformal and has analytic on your dimension.
This is precise. But in higher dimensions is also interesting because composition of matrix is also interesting.
Right.
Yes, but you can simply say that you consider C1 plus theta or conformal.
Right. Okay. Well, so but formally in our case we consider C1 plus theta conformal maps. I will stick to them. Okay. But of course, even in higher dimensions, when you have conformal systems with overlaps, still things are very interesting.
Yeah, matrix is also a system of matrices.
Okay. And in particular, it doesn't have to be well linear in higher dimensions.
No, it's matrices.
It's matrix, yes.
Linear and wider set.
Yes. Okay. What we want to do is we want to endow the symbolic space with a certain metric. Okay, and this metric will come from an IFS, so I call it a metric adapted to an IFS. I denote it by rho f. And the way it operates is the following. So you take two distinct infinite sequences. You look at the longest common prefix, which I denote by omega watch tau. You look at the composition corresponding to this finite word. Okay, this longest common prefix. You have your map, and you look at the norm of its derivative. Okay, and if this will be something exponentially small in the length of this longest common prefix. Essentially, or maybe another way to think about it is that this metric, this is essentially, or I don't know, up to some constants, the diameter of the image of the whole space or of the attractor under the map corresponding to the to this longest common prefix. Okay, so basically what you do is you have your 2 points, you look at the smallest cylinder that contains both of them, and you look at how large is this cylinder. A nice thing is that this map by f is Lipschitz in this metric. Okay, and now this map will be B Lipschitz if the system satisfies the strong separation condition, which means that the images of the attractor are just disjoint. Okay, and so this case, from the point of view of the dimension of the measures and the measures on the attractor and dimension of the attractor, this case is somehow not very interesting because everything gets preserved under the Lipschitz. But nevertheless, this is the case. Now, we want to study some measures, first on the symbolic space and then on the attractor, by E sigma sigma. Well, by E sigma sigma, I will denote the set of all shift invariant ergodic Borel probability measures on the symbolic space. Okay, and now once you have the notion of a metric in the symbolic space, you can ask about the dimension. Let's say the Hausdorff dimension of a measure with respect to this metric. And it turns out, this is another nice thing about this adaptive metric, is that this dimension in the symbolic space is given by dynamical invariance of the measure. So this is entropy over the Lyapunov exponent, where entropy is just the usual Kolmogorov-Sinai entropy of the measure mu in the symbolic space. And chi mu, the Lyapunov exponent, is given by this integral. So this is integral of the potential, which is, minus logarithm of the norm of the derivative of the first map of your sequence, evaluated in a certain point. And if you haven't seen it before, it's actually quite easy to see, or at least morally to see, where it comes from. So we look at almost every point in the symbolic space, and recall that to calculate the local dimension, we have to compare logarithm of a small bore to the logarithm of the radius, right? But now in the symbolic space, instead of looking at the balls, we will look at the cylinders. Okay, so we compare logarithm of the measure of a cylinder to the logarithm of the, let's say, diameter of the cylinder. And now, so here I just divide by 1 over, and so I do nothing. And now we can apply ergodic theorems. So the Shannon-Macmillan-Brayman theorem, so the ergodic theorem for entropy, tells you that, the measure of a typical cylinder as n goes to infinity scales like, e to power minus n times entropy, right? Or in other words, or maybe precisely, this thing goes to the entropy, and then Birkhoff-ergodic theorem applied to the function under the integral, together with the chain rule, I guess, for the derivative, gives you that. Well, okay. First of all, essentially by the definition of the metric, the diameter of a cylinder is essentially this derivative. Okay, maybe up to some constants or things like that. And then you can apply the Birkhoff-ergodic theorem to this potential, and this will converge to the Lyapunov exponent. So this is where this formula comes
What
from.
about the infinite number of symbols?
Oh, that's a different word. That's a different word which we do not cover here.
It's interesting.
So there are definitely
For finite dimension does
Right.
not depend on configuration.
Right.
If they are separate. Infinite,
Yes.
it is not that.
I think this is still true if both things are finite.
Yes.
I think that this is known
If
to
both things
I mean
are
entropy and the
finite, but
Lyapunov
infinite
exponent
iterated function system.
for infinite iterated function systems. I think, but maybe I'm confused.
It will be close.
Okay, so this is the dimension of a measure. We would also like to talk about the dimension of the set, because we can talk about the dimension of the whole symbolic space with respect to this strange metric. And this turns out to be equal, maybe here I won't get that much into the details, but this turns out to be equal to the zero of the pressure, again corresponding to the geometric potential. Okay, and then it is known that the Hausdorff dimension, and what's important for us, the Aswad dimension as well, of the symbolic space with respect to such a metric is equal to this number, which is defined as the unique zero of this function, which is this pressure. Okay? Yeah. And now, so somehow similarly to the Marström theorem, the question is, this is, I guess, the main question in fractal geometry, or definitely one of the main questions, is when under the projection, so when going from the symbolic space onto the attractor, these are usually the objects that we actually care about, the ones that live on the attractor, on this geometric object, whether they do not lose dimension under this projection. Right? So again, the question is, so recall that D is the dimension in which the IFS is defined. So again, any object on RD will have dimension at most D. And then again, this map is Lipschitz in our metric, so it can only decrease the dimension. So again, the question is, well, I guess for which systems the projected measure and the attractor have the maximal possible dimension, which is given by this formula. And now at least you can understand where this formula is coming from. Okay, so this is somehow the question. And now the fact of life is that if you have a system with overlaps between cylinders, so not satisfying the, let's say, the strong separation condition, this might lead to a dimension drop. Okay, so it's not difficult to come up with systems for which this inequality, so in general we have an upper inequality, and sometimes it can be strict. Okay, but somehow what turns out, and what people are often after, is that in many families of iterated function systems with overlaps, so now instead of a single system, think of maybe again a family of systems which depends on some parameter. It can be proved in several, in many cases, that in such families, despite there are systems for which the dimension drop, for typical systems, the dimension formula will hold. So it holds typically or generally.
Excuse me, so just to check, you see the example, if we take one map and repeat it, say 2 times, it will be...
That's the easiest example. That's the easiest example. Because then if you just have a single map repeated many times, then the attractor is just a singleton, which is the fixed point of this map. But in the symbolic space, well, you have some maybe large entropy and Lyapunov exponent and so on. There is, yeah.
You don't have to be the same maps, they just have to have the same fixed.
Right. Yeah, that's true. That's true. Or for slightly more sophisticated cases, you can take systems in which, well, maybe the maps do not repeat themselves, but what happens is that maybe in some higher iterate of the system, two different compositions are just the same, right? They are equal. And then this can lead to a dimension drop, and actually for, well, self-similar systems, so IFS is consisting of similarity maps, there is a conjecture which says that these are possibly the only examples which lead to dimension drop. Okay, so now I will talk about a by now classical, I guess, technique of proving this sort of statements, which is called transversality. And the sort of general theorem that we prove will be a universal version of the projection theorem for transversal families. Okay, this is what we will be after. So what is transversality? So now assume in the context of iterated functions. So assume that we have a parameterized family of IFSs, conformal and or C1 plus theta, and it depends on some parameter. And for short, I will denote by pi lambda the projection from the symbolic space corresponding to the system f lambda. I assume that they are all over the same alphabet. Okay? And we want to talk about typical parameters, so I want to have a measure on the parameter space. So U is a parameter space, and eta is supposed to be a finite measure. And now there is a condition which is called the transversality condition, which says the following. So there is a constant C, and such that for every R, whenever you take two symbolic sequences which are distinct, but even more than that, they are distinct already on the first coordinate. Okay? And then what transversality tells you is it tells you that the set of parameters for which those two faraway points in the symbolic space get projected too close. Such a set of parameters is small in a certain quantitative way. So what it says is that the set of lambdas such that the distance between these projections is at most r, is at most some constant times r to power d. Okay? This is a transversality condition. Now, somehow, maybe morally where it comes from a similar inequality for orthogonal projections. Okay, so for orthogonal projections, there is a classical inequality like this. And now if you think, so here x and y are arbitrary, but if you think that x and y are in some definite distance, then you get an inequality like this. Now a big difference is that while for orthogonal projections, this is just a theorem, this isn't just an inequality which holds. For a given family of iterated function systems, you have to check whether this transversality condition holds, and it doesn't hold for all families. Okay, so there are many examples where it holds and many examples where it doesn't hold. But once it holds, what you can do is you can try to essentially repeat the proof of the Marstrand theorem, and this gives you some result on the dimension of invariant measures. So here is a statement of a theorem, or a consequence of a statement of a theorem by Szymon, Solomek, and Urbański, who have, well, this is as far as I know, the first kind of general statement of this transversality type result, but definitely the technique goes back to early 90s for some particular cases. So I assume that I have a, continuous family of C1 plus theta conformal IFSs, which just means that the maps in the IFS depend on lambda continuously in the C1 plus theta topology. Okay, these are technicalities. And now we fix a measure, ergodic measure in the symbolic space. Any ergodic measure, but fixed. Okay? And then if the transversality condition holds on U, this is the statement of the theorem, then for almost every lambda, we have what we want to have, that is the dimension of the projection is the maximal value that it can take. Okay? And now, okay. So before I tell you how we can improve this, some examples of families which satisfy this transversality condition. So maybe the most famous one is Bernoulli convolutions. So this is a system of similarities on the unit interval like this. They depend on the parameter lambda, and interesting things happen for lambda greater than 1/2, because then these two intervals start to overlap. Right? And then the attractor is just the unit interval, but so the attractor is trivial, but the projections of invariant measures can be highly non-trivial. and it satisfies the transversality condition on a certain sub-range of the parameter space, okay? Up to 0 point something like 649. But it doesn't satisfy the transversality condition on the whole interval, okay? So this is somehow the limitation of the technique. And another one maybe more interesting for us today is a translation family. So what you do is you fix just any C1 plus theta conformal IFS. Okay, here I stated interval, but this also has version in higher dimensions. But you assume that these maps have strong enough contraction. This can be weakened, but for the sake of presentation, let's say that the derivatives are smaller than 1/2 of all of the maps. Okay? And then what you can consider is you can consider a parameterized family of sort of translated IFSs where, well, just what you do is just to a map fj you add a translation by lambda j. Okay, and the vector of lambdas is now some higher dimensional parameter. Okay, and this family will satisfy the transversality condition. So these are some examples. Now I feel obliged to tell you that there are, for some years now, there are, at least for some questions, there are stronger techniques on the market. So the ones that go back to papers of Hoffman, which are, well, which have the advantage that they are able, usually, once they are applied, they are usually able to cover the whole range of parameters that you are interested in, and they give you better bounds on the exceptional set. So not only saying that the set of bad projections is of measure 0, but maybe saying something about the dimension of those sets. Somehow the problem is that this technique seems to be rather difficult to apply to more general cases than so far. So the basic one.
What transversality condition? In this technique, you have.
So no, it does not use transversality. So these techniques do not use transversality. This is a different technique based on additive combinatories. This is I guess that this is a completely different, in a sense, thing.
Jordan and Rappaport are two people.
Jordan and Rappaport are two people. Actually, today your result we will get in a moment.
But this is not Jordan.
No. This is Thomas Jordan from Bristol.
Okay.
I don't think that he's 200 years old. It was also able to cover self-affine case, and very recently and very excitingly, also the real analytic case on the real line. This is a recent preprint by Ariel Rappaport. But nevertheless, somehow the lower regularity on the interval is not covered yet. But what is interesting for us is the result of Jordan Rappaport, which is a sort of a universal result of this sort, okay? Which tells you that if you have a self-similar IFS on the real line, which satisfies the exponential separation condition, let's leave that for a moment, then the dimension formula holds for all ergodic measures at once, okay? And now, I don't want to tell you what this exponential separation condition is because it really doesn't matter for us today. But I want to tell you that if you treat lambda and t as the parameters, then this condition holds not only on a full measure of parameters, but actually the exceptional set has non-full Hausdorff dimension. And moreover, this condition can be verified for some particular systems. Okay? So in this regard, this is better than transversality, but still transversality has some flexibility in applying to different problems.
Zero Hausdorff dimension would be too small.
This is this parameter space here is large dimension because it's something like twice the dimension of the space, and I think that the statement then is that it's of codimension 1. On the real line, for example, if there would be only one parameter, then indeed you get Hausdorff dimension 0. Okay, actually proving that this exponential separation condition holds on such a large set, this uses some sort of transversality. But this is much weaker, and this is another story. And it's a different, somehow the purpose of transversality here is different. Okay, here is our result. which what it does, it basically bridges a gap in the sense that it brings this type of result, so this sort of universal for all ergodic measures at once, to the transversality. Okay, so the result, so the assumptions are exactly the same as in this result by Szymon, Solmek, and Turbański. So we have a continuous family of iterated function systems, and if the transversality condition holds, then, well, for almost every parameter, the dimension drop does not occur for any ergodic measure. Okay, so we go from a fixed ergodic measure to all of them at once. And moreover, and this is somehow important for the applications, we again have the universal version of this probabilistic Aswad dimension embedding theory. Okay, so it simply says that again under the transversality for almost every parameter, such that the similarity dimension of the system, so we call that this is the zero of the pressure, which is the Aswad dimension in the symbolic space. If this is smaller than D, then the natural projection map again is mu nearly Lipschitz with respect to this adapted metric on the symbolic space, and again this holds simultaneously for all measures. Okay, and now I should say, okay, maybe I have something here. So this mu nearly Lipschitz condition for IFSs or the natural projections map is given in terms of the regularity of this inverse to the natural projection map, but there is a formulation which is given as some sort of a separation condition directly for the cylinders on the attractor. So this is equivalent to a notion which was introduced by István Kolozsvár and Károly Szymon in a note which they didn't publish. And they called it exponential distance from the enemy. Now, maybe I don't want really to get into the details, but it tells you something about what is the distance between, well, you look at all the level and cylinders, you look at your point, and now you look at the distance of your point from all the n-level cylinders or the other n-level cylinders, okay? And you need to have some bulk on that. So this is some sort of rather strong separation condition for the cylinders on the attractor. Okay, and hence, well, this distance is exponential, and if you are omega, then your enemies are guys in all the other cylinders. This is why exponential distance from the enemies. And what's important is that we can do it in this sort of universal fashion for all measures. And now, so let me again concentrate a bit more on this condition, because I would like now to tell you something about the applications of this plot. Okay? So okay, Rico, here is the definition, right? We have for natural projection maps, we have this Helder inequality for the inverse, but the point is that it holds only for almost every omega, with a constant which depends on omega and it depends on alpha, and alpha can be as close to 1 as you wish. Okay? And okay, in this notation it also depends on lambda, but this doesn't matter. And now a nice thing about this property, this property, is that it gives you the following, that so whenever you have such an inequality, whenever you have this condition at given omega, then whenever you take any finite measure mu on sigma, any finite measure, then the pointwise dimension, upper or lower, but the local dimension of the measure in this point gets preserved under this map. Okay? Meaning that the dimension of the projected measure at the projected point is equal to this. Now, here I have a proof, or a sketch of the proof. But let me just tell you that, well, it just follows from the fact that if you take, due to this inequality, it's simply the thing that if you take, so let's say that here we have RD, somewhere here is sigma, here I have omega, and now if I look at the ball around the image of omega, the R ball, then its pre-image will be, well, contained in a ball around omega of radius c r to power alpha. Okay, and this allows to tell you, but now a measure of this ball is something like, well, this radius c r alpha to the power, this local dimension of omega, which is something like r to power alpha d of omega, right? But if you can take alpha arbitrarily close to 1, you are done. This is somehow the philosophy. So this is a very nice thing, because whenever we have a point where this holds, then local dimension of any measure gets preserved in this point under the projection. And this allows us for some applications to multifractal analysis. So now let me try to give you, well, just a short introduction, just a few words on what multifractal analysis is. So we look only at self-similar, IFS is consisting of similarities. So let's say that we have a system consisting of similarities on R, okay? And we fix a measure in the symbolic space, let's say Bernoulli measure. Okay, so then the projected measure is called a self-similar measure, right? And now recall that the similarity dimension of the system is the, well, 0 of the pressure, but in this case, this is equivalent to satisfying this equation. And we assume that S is smaller than 1, so in particular this asphalt dimension is smaller than 1, we can apply the previous theorem. And we assume that somehow the situation is not degenerate in the sense that the probability vector is not equal to this probability vector. Okay? Otherwise, there is really nothing to talk about on what I'm going to talk about. And now what a multifractal analysis aims is determining the so-called multifractal spectrum, which does the following. So you look at your measure, and now we know that, well, at typical point x with respect to this measure, the local dimension will be equal, well, to the dimension of the measure, okay? But still, there might be, and there, well, in this case, there will be plenty of other points in the attractor, which are, well, not seen by the measure mu, but the local dimension of this measure attains some other values, some value alpha, let's say. And now, here I cheat a bit. This is not how usually people define these things, but for us today, this will be good enough. So I will say that the multifractal formalism holds if, well, this multifractal spectrum of the measure mu, it holds at alpha, well, if the dimension of this set agrees with a certain value coming from what you can calculate in the symbolic space, okay? So just as we had these heuristics for the dimension of a measure, which is entropy over Lyapunov exponent, which was coming from the analysis in the symbolic space, for this spectrum in the symbolic space, you can perform a similar analysis, okay? And it leads you to a conclusion that you might expect that the Hausdorff dimension of this level set should be equal to the Legendre transform at alpha of a certain function, and this function t of q is defined using a similar, well, a condition which is somehow similar to this one. Now, I will not attempt to explain to you where this formula comes from. Just believe me that if you do a calculation in the symbolic space, this is somehow what pops out, okay? And the question is whether this gets preserved under the projection. And now the range of alphas on which this is interesting for a given self-similar measure is given by this formula. And now there is a result by Bárány and Feng, a recent result, which tells you that if the similarity dimension is smaller than 1 and system satisfies this exponential separation condition, which I haven't defined for you, but we know that it holds typically in a strong sense, then the multifractal formalism holds on such an interval, okay? So the point is that they were unable to cover the whole interval, which, I will say something, it might not make sense to some of you, but maybe to some of you does. The range which they cover corresponds to the positive part of the LQ spectrum, okay, for Q positive. The remaining part is the negative one, okay? And what we can do with the use of this nearly Lipschitz condition is to, well, fill this gap, so we can cover the whole spectrum. The price to pay is that because we use transversality technique, we don't quite know how to do the same with Hofmann techniques. Because we use transversality technique, we just get it for almost every parameter in the following sense. So what you do is you fix lambda, so the contractions, and then you vary the translation. And then for almost every translation, you will get that the multifractal formalism in this sense, okay, in this sense, holds on the full spectrum. Okay?
But every P on the interval, what is this?
Right, so P is this. So actually for almost every IFS, this holds for all Bernoulli measures at once.
Okay.
Now, so this somehow is able to deal with this negative part of the RQ spectrum. So in terms of the exceptional set, this is not as good as Bárány would think, but well, it's still better in the sense that it covers the whole range. And now how we prove it? What's the idea? Of course, I will not give you the proof, but somehow the idea, I will try to convince you that this Bilipschitz property, this merely Bilipschitz property is useful here. So remember this. This tells us that in our setting, which we can, so that our theorem which we can apply to this setting gives us that for any measure at almost every point with respect to measure, the local dimension at this point of any other measure will project to what we want to project. And the way it is used morally is the following. So, well, the philosophy is that we know how to do things on the symbolic space, and we want to understand that this doesn't get spoiled when we project down to the attractor, right? And what you have in the symbolic space, which is essentially how this calculation is done on the symbolic space, which I haven't showed you, is that you distribute a certain measure on the symbolic space, which depends on alpha. I denote it by mu alpha, and you choose this measure in such a way that entropy over the Lyapunov exponent for this measure, so the dimension in the symbolic space, is equal to whatever the T star of alpha is. And there is, if you want, there is an explicit choice, okay? And now, moreover, you do a second calculation using how this measure was constructed, and you see that not only this holds, but also for almost every point with respect to this measure mu alpha. So think of mu as fixed and maybe alpha as varying, but for almost every point with respect to this measure mu alpha, the local dimension of mu, the measure that we want to study from the multifractal perspective, is equal to alpha. Okay? So this, what does it tell you? So this immediately tells you that in the symbolic space, the dimension of the level set has to be at least the dimension of mu alpha. But the dimension of mu alpha was chosen such that this holds. So this gives you the lower bound, which is somehow the more difficult part as usual. But now we can apply our universal projection theorem, which says that for almost every t and all alphas, because we can deal with many measures at once, the dimension of mu alpha under projection gets preserved, so it is equal to it. It gets preserved because we assume that the dimension of the whole space is smaller than 1. So when we project to 1, the dimension doesn't shrink, right? And this merely Bilipschitz property tells you that also at mu alpha, almost every omega, well, this equality gets preserved, namely that the local dimension of the projected measure at the projected point is equal to the local dimension of the original measure. But this was alpha. This was equal to alpha. So again, this tells us that the dimension of the level set, so we have found a measure which lives on this set, right? The measure which is projection of mu alpha. So the dimension of this set has to be at least the dimension of this measure, but the dimension of this measure is equal to T star alpha, what we wanted it to be, and this is the lower bound, and this is somehow the problematic one. So you see how this merely Bilipschitz property interfered here, and maybe I should emphasize that, even though these additive combinatorics methods of Hofmann are usually stronger than transversality, especially for self-similar measures, still well, still with this result we can beat this additive combinatorics methods using transversality, at least for now. Okay, so I've been telling you that there are those two settings, the orthogonal projections and the IFSs, but we also, first of all, in order to be able to apply the results to both of the settings at once, and also for some other possible generalizations, we wanted to put this results in a general setting. So now I will talk about these generals. I still have some time left. So my last goal, I guess, is to explain to you somehow what we can say in the general setting, and in particular, what is the condition on the family of measures n that we use, right? Because so far we were just saying, okay, this holds for ergodic measures, but why? So I will try to explain this at least a bit. So the general setting will be as follows. So this is some sort of a generalized transversality projection scheme. Okay? So let X be a compact metrizable topological space. This is the space from which we will be projecting. Okay, so for IFS is the symbolic space. Now I am saying metrizable instead of metric because I want to allow the metric which we consider on X to vary, right? Just as we had to do with this adapted metric to the IFS. U parameter space. Formally, it is enough to assume that it is hereditarily Mendeleev. You can think that it's separable metric space. Okay, that's enough for all our applications, but formally, this is enough. Eta, this is a measure on the parameter space. So the almost sure statement with respect to eta. I want it to be locally fine. You can think fine. Pi lambda projections. So now I just assume that I have a family of maps from X to Rd, which depend on lambda. Okay. Soon, of course, some continuity will be assumed. And now rho lambda. So each lambda, each parameter, possibly gets its own metric on X, which is compatible with the topology, just as we've seen in the symbolic set. And now, we have to make some assumptions. So first some technical assumptions on this whole scheme to work. I won't be really getting into the details, but just to give you a feeling of what type of assumptions are here. So first of all, we assume that each map is Lipschitz in its corresponding measure. Okay, so far so good. Now, okay, we want to assume that this matrix rho lambda, if they depend on lambda, they need to depend on lambda in some regular way, which essentially says that, okay, locally in the parameter space, when you perturb lambda, this matrix change, again in a sort of nearly Lipschitz way. Here is a statement, I really don't want to get into it, but this is technical, and in our cases, either rho is fixed and then there is no problem, or it's just easy to check. The actual eventual assumption is transversality. Okay, and now again, we can relax the usual transversality a little bit. Maybe again, I don't want to get into it. Just think that essentially something like this condition.
But there was the additional delta, did I see?
Yes, so actually in an abstract space, this condition doesn't make sense. So I want to say that X and Y are in some distance delta. Okay?
Oh, okay.
So, okay, we can take a look at this once we get there, which is enough. Okay? So you look at points which get projected too close to one another, but X and Y are in the distance at least delta, and actually the dependence on delta is allowed to blow up to infinity as delta goes to 0, but only slower than delta to power minus epsilon for atoms. Okay? This is a technical extension of transversality, but actually this thing allows us to cover some non-autonomous iterated function systems where this sort of weaker version of transversality holds, and it's general enough to apply here. Okay, but from the point of view of our talk, this is some technical nonsense. But yet this technical nonsense is general enough to include orthogonal projections, conformal IFSs, and also, so these examples that we've seen, also some non-autonomous and random IFSs, and hopefully some other things as well. But now we get to the more interesting stuff, right? To what we assume about these collections of measures. And now, so first some notation. By n phi of x, I will denote the collection of all finite Borel measures on x. And for a moment, fix a metric on x. And first, so there are two assumptions that we want to make on the measures. One is technical, and basically we have it for free in all our examples, but in the general setting we have to assume it. And the other one is the actual assumption. Okay. So first the technical one. So we say that a measure mu, finite measure mu, is weakly diametrically regular with respect to measure to metric rho, if for almost every point with respect to this measure, this thing holds. Okay, this limit is equal to 0, which simply means that at almost every point, so at almost every point, for arbitrary small epsilon, inequality like this, so you look at the measure of ball, which is twice the radius, is at most r to power minus epsilon measure of a ball. And this is supposed to hold for every epsilon for all r's small enough. How small is r is allowed to depend on epsilon. Okay? So this is something, this is like a weaker brother of the doubling condition, which would say that this is actually some constant, at most some constant. And now in the Euclidean space, this is a non-trivial condition, but this is actually a trivial condition. So two facts. I mean, okay, trivial in the sense that it holds, maybe not trivial in the sense that you see it right away. So if you have a measure for which the pointwise dimension holds, so the local dimension exists at almost every point, so the upper and lower limits coincide, then it's easy to see that this measure is weakly diametrically regular. And this is the case for every ergodic measure in the symbolic space, or even every invariant measure, I guess, in the symbolic space. And also every finite Borel measure on Rn is weakly diametrically regular. Okay, this follows from, I guess, maybe Bezikovich covering theorem and some Borel-Cantelli type argument. So this, in all our cases, measures will satisfy, in all our applications, measures satisfy this essentially for free, so this is not a problem. And now I want to formulate this non-trivial condition, and it's given in terms of something that we call, a notion which we call relative dimension, okay? And here is the definition. So what you do is you fix two measures, mu and nu, and you want to define the relative dimension of mu with respect to nu, given a metric. And we denote it with this symbol, being mu relative to nu with respect to the metric rho. Well, and it's defined here. So essentially what you do is you want to look at ratios like this, logarithm of the ratio of the balls compared to the logarithm of r, and you want to see, well, essentially the lowest and the highest value and the largest value that you see in the limit, typically with respect to measure mu. This is what it says here. Maybe, I guess, well, for me the way to think about it is the following, and this is actually what you use. So if you have two measures such that this relative dimension is smaller than epsilon, then for almost every mu, almost every point, you have such an inequality between measures of balls. Okay, so we can compare measure of a mu ball with measure of a nu ball up to a error which is of this order r to power minus epsilon from above and from below. And this is now, but this doesn't have to be uniform, so for almost every x, this holds for r small enough, but how small this depends on x and epsilon. And if you want to make it uniform, you have to restrict to a set of almost full measure, and then there are some games that you can play, but also some problems that you have to avoid.
Saying this for mu almost every x is of course completely different than saying this for mu almost.
Exactly. So you should think that these are two mutually singular measures. Okay, so a priori, saying something about mu almost every point doesn't tell you anything about nu almost every point. Okay, maybe I can give you an easy example when of two measures which are close in this sense in the relative dimension. In the relative dimension, take two Bernoulli measures in the symbolic space with probability vectors which are close to one another, right? Then this will hold. Now, so this is something. This seems kind of arbitrary. The way, at least again somehow the way we arrived at it is by analogy with the Kullback-Leibler divergence or relative entropy for ergodic measures. So this is somehow really the story was that we were first able to prove things in the symbolic space using relative entropy, and then we wanted to somehow mimic this geometrically in Euclidean space or other spaces, and this led me to
Who is Leibler?
Sorry?
Who is Leibler?
Well, I don't know, the guy who worked on
Because I
Kullback-Leibler.
had a friend here in my head who actually became a physicist, emigrated, and became a very famous physicist.
Maybe
I think
it's a very classical notion in information theory. I don't know. Definitely.
Is when you take like two potentials and look at the Berkov behavior of the Berkov spectrum of one potential from the point of view of the Gibbs measure sitting on the other potential, and something like this.
Definitely. So this idea to use relative entropy in this context in fractal geometry, this is definitely not new. This has been around for a long time. I guess what we did is we realized that it can be used to improve to this sort of universal thing, which as far as I know haven't been noticed before. Yeah.
So I wonder, is it simple to think about example when relative dimension, when you switch mu and mu becomes very different? It's not symmetric,
right. It's definitely not symmetric. I guess it should be so. So one problem arises when so this I haven't said, but if the measure, so I guess if you have two measures which have different supports, so I guess maybe an example would be something in the spirit of this, that you have maybe a measure, I don't know, mu or nu, which has support like this, and then you have mu, which has strictly larger support, okay? And then the problem, you see, the problem with this quantity is that if you take a mu typical, so maybe this should be the other way around, yes. If you take mu typical point, which is outside of the topological support of nu, then actually you have problem with this quantity because you have to divide by 0, right? And then by convention we just set this dimension to be plus infinity. It's just not well defined. But vice versa, it could be finite, I think if you take...
Can you give an example when the two measures are ergodic and still the distance is... Good question.
I think it should be possible.
Mutually singular.
So...
Some ergodic,
different. So non-mutually singular are somehow not very interesting from this perspective. Well, okay. Let me tell you what I know. I know that there are for relative entropy, which is definitely this. And if I have time, maybe I will tell you something about relative entropy. There are examples of ergodic measures. Of full support, for which at least, this thing is not well defined in the same sense. No, this cannot be true. No. I think it's still, it is well defined by, I think, equal to plus infinity or something like this. The problem is that if you have two ergodic measures, I would have to think about it a little bit, because
relation to pullback library, just by analogy, or in a certain context is the same?
So in the certain context is the same. So if you take the measure on the ergodic measure on the symbolic space and you take a suitable metric there, these two things will be the same. And the fact that these two things will be the same, actually the definition of relative entropy is slightly different, but the fact that they are the same will follow from what's known as the ergodic theorem for the relative entropy. So there is somehow a step hidden here. Okay, but but the answer is yes. The answer is yes. Okay, I will have to think about examples. Now so this is some sort of because of this in general lack of symmetry, you cannot think of this quantity as a distance between mu and nu, as a metric, right? But still what we do, but the philosophy that we have is that so now I will talk about this condition that we want to impose on a family of measures, right? And morally, the condition is separability with respect to this metric. But this is not a metric, okay? But this doesn't scare us away, so we say that a collection M of finite Born measures is a relative dimension separable with respect to a given metric if there exists a countable set V of finite measures which has this property that for every measure mu in our collection and every epsilon you can find a measure nu such that this inequality holds. And of course here the order of mu and nu is important and it is supposed to be like this, okay? So this is what we call maybe by some slight abuse of language, relative dimension separability of a class M. Now, some examples, and these are somehow examples that allows us that together with the theorem that we will follow justifies all the statements that I've made during the talk. So if you have your favorite conformal IFS, a fixed conformal IFS, then first in the symbolic space, the space of the set of ergodic measures is relative dimension separable with respect to this adapted metric. Okay, this is somehow the mother of everything that follows. But we can also somehow study this condition under the projections, and so we see. So this is essentially a trivial statement. Given this, that if F satisfies the strong separation condition, then also the space of all the projections of ergodic measures. So all the ergodic measures on the attractor is relative dimension separable now with respect to the Euclidean metric. This is not very surprising because, as I told you, if the strong separation condition holds, then pi f is Be-Lipschitz, so well, it preserves everything that we want. What is maybe less obvious is that if we take G to be the collection of all shift invariant Gibbs measures which correspond to Haber continuous potentials on lambda. This is again a huge uncountable family of measures, and then we can say that without any separation, the family of the projections is relative dimension separable with respect to the Euclidean metric. Okay? And now, so here comes this sort of general result, which now we should be able to follow. So we make this, well, A1 and A2, so technical assumptions on this projection scheme.
Stupid question.
Yes.
If you have something, how does projection which is not by issue, but
Right.
you should work on this condition?
Right. So the point is, so I don't really have an example showing that it destroys, that the Lipschitz projection destroys this thing, but I was unable to prove that it preserves the thing. What I was able to prove is that if you have a family which satisfies a stronger condition, which is basically a sort of a uniform condition, where you can take this uniformly among x and epsilons, basically, then, and this is something that the family of Gibbs measures satisfies, then under the projection, so the projection again, I am unable to prove that it satisfies again the stronger uniform version, but it satisfies this weaker one. So this is essentially how this. So by the weaker one, I mean just this one. Okay, so this is how this is proved. But I would expect that arbitrary Lipschitz projection is able to destroy it. I would say so. But this is just a guess. So technical assumptions plus transversality. We assume this is the main assumption that n is relative dimension separable. And another technical assumption is that each measure in the family is weakly diametrically regular with respect to, and now both of these conditions are supposed to hold with respect to every metric that we have. So this seems strong, but actually because of this continuity that we assume of the metrics, really if you check it at one metric, then it also almost holds in the neighborhood. This is technical that we deal with all the metrics. And the statement is, well, not surprising at this point, I guess. So we say that for almost every parameter lambda, when we look at the projection, we have that the analog of the Marston projection theorem for upper and lower Hausdorff dimension, and also this probabilistic Aswad embedded dimension. All of this holds for almost every lambda for all mu simultaneously. Okay? Yeah. And this is somehow the general statement. And now I have 3 minutes left. So maybe I will just give you a tiny glimpse. So I won't be able to talk about the proof of this, but just a tiny glimpse into this condition of relative dimension separability of ergodic measures. So now I will tell you something about the Kullback-Leibler divergence. So now given two ergodic measures, the relative entropy of mu with respect to nu is by definition this limit. Now, in general, it doesn't have to exist. Okay, it doesn't have to exist, but if it exists, then we take it. And you see that it's kind of similar expression, log mu over log mu, but instead of essential supremum and infimum, we take the integral, the average, right? So this is somehow an average version of this. But nicely for us, there is an ergodic theorem for relative entropy. Now again, this ergodic theorem doesn't hold for all Kirchhoff measures, but it holds if the reference measure, so mu, is a k-step Markov measure. K-step Markov measure just means that the distribution of the k plus one step depends only on the first k values, right? And moreover, so for it even to consider this ratio, we need to assume that n-dimensional distributions of mu are absolutely continuous with respect to n-dimensional distributions of mu. But if this holds, then at mu almost every point, this ratio converges to the relative entropy. Okay? And this essentially tells you, so if you go back to this definition and use this heuristics that balls are essentially cylinders, this gives you that relative entropy is essentially maybe up to a constant depending on the metric, or on a nice metric on the symbolic space. This is this relative dimension, and I guess if you choose a proper metric, which is something like 2 to the power minus the length of the prefix, if this logarithm is in the base 2, then you actually have equality. Okay? Now, so the goal is really, for ergodic measures, is to find a countable and relative entropy dense set in the ergodic measures. And I set here k-step Markov measure. You can see where this goes, right? So what you do, there is actually a well-known classical fact from information theory that any ergodic measure can be approximated in this relative entropy. So the relative entropy will go to 0 for a sequence of measures, mu k, such that each of them is Markov measure. Okay, mu k is a k-step Markov measure, and actually you can take here what's called the k-step Markov approximation of mu. Okay, it's a certain way to choose a Markov measure which approximates mu, and this approximation is good in the relative entropy sense. So this essentially means in our language that Markov measures are relative entropy dense in in ergodic measures. But of course, Markov measures, this is an uncountable set. But the way to find the countable set is just to take Markov measures with rational transition kernels. Okay, so the transition kernel, this large matrix, it is supposed to have only rational values. And moreover, the relative entropy, once you fix the length of a step, the relative entropy is essentially depends continuously on the transition kernel. So this means, essentially, this gives you that V is also relative and is a countable relative entropy dense set in Markov measures and also in ergodic measures. This is okay. This can be made rigorous.
Are these Bernoulli measures also relative entropy dense?
I don't think so.
Is sigma fixed? Or number of symbols when you have
Number of symbols is
grow?
fixed. Number of symbols is
Because
fixed.
if it grows, we can.
If it grows to infinity, that's
we
another
can do
story.
everything.
And then, I don't know, maybe, I guess something can be said, but I don't know what.
Markov is helpful. Not Bernoulli.
Yes, so if Bernoulli measure, if by Bernoulli measure you just mean,
For
an
iteration.
infinite, so for iteration I think yes, but Bernoulli measure, but then it's
No, the original Bernoulli, of course not, but
The original
I'm
Bernoulli.
talking about Bernoulli for iteration, that is you take the k words,
right, and then you
Bernoulli
repeat.
measure on them, you get a measure which is sigma k invariant, not
Yes.
sigma invariant, and you take the...
You take the average.
Yes.
I think that if you take the average, I think that then the answer is yes. I think it should be more or less the same. I think so. Okay, so the proof. Okay, thank you very much. Thank you.
Are there any questions?
It's not that the first place where this transversality was applied in higher dimension was Szymon Sołomek-Bański. I think it was known before. It's one of the papers of Perez Szymon Sołomek, I guess. I mean, I was making my PhD in 1999, and by this time it was already
Right.
known.
So the only claim
Károly can tell us.
right.
So I didn't hear completely. It was 19. Yeah, I understand the question. It was Perez and Solomiak and in 90s.
Adam was saying that the first paper to show the higher dimensional version of transversality was your paper with Sołomek and Urbański in 2001, but I think it must have been earlier than that.
Higher dimension.
Actually.
Maybe I have to tell you that I don't quite remember for the higher dimensional. Maybe earlier. There was definitely something earlier in parts, but I do not remember completely without having in which detail. But in higher dimension, I believe there was something earlier. I believe.
I even had this in my PhD, and it was 99. But
So-
it was not proven by me. It was already known by this time.
So what I think might be true is that the sort of general statement where you just have a parameterized IFS, some conditions on it, and transversality assumption, I think that this sort of general statement might have appeared first in this paper. I'm not saying that
No,
definitely.
I definitely had the higher dimensional transversality condition, that's exactly the same version that you write
Okay,
in my
so
PhD.
okay. So from now on, I will be writing MRAMS
claim to be
1999.
the discoverer of this method.
I guess it's just a matter of.
No, I don't remember what I did. That was another thing, but also in higher dimension.
So-
We discussed because I was his advisor.
So
And
definitely,
the copy is here in the library. You can check.
The idea to use transversality as such diaphysis, I think, goes back to Károly and Mark Policott, right? This is
I guess folklore.
yeah.
Okay, when you go to higher dimension in the orthogonal situation, everything
Works the same.
works the same.
Yeah, it's just a matter where it was
The
written
both.
first to have a reference, I guess.
Are there any other questions, or maybe historical or not? Maybe online? Okay, if not, let's thank Adam again.
Thank you.
Speaking the same idea, there's some